Ah, look at you. You're taking a journey with me, and that journey is through the ion chromatograph. So we've already made a couple of pit stops along the way, and we've talked about the mobile phase, and we've talked about the inline filters, and we've talked about the main pump that pumps my mobile phase, and we've talked about the injection valve, and every consumable up to this point that can be changed, replaced, or touched by you. So you can make sure that you have a very clean system to use every day in the lab. All right, so what happens after the injection port? Well, the next piece that we're going to talk about is going to be our column. Now, you're probably wondering, oh no, what is he going to go on and on and on and on and on about a column for? We already kind of know what the column's purpose is. If you don't know what the column's purpose is, then you've not been paying attention throughout the entire course so far. Because the purpose of the column is just like it is in any chromatograph system or any type of chromatography technique that you want to bring into the lab. The column's purpose is for separation. Its true purpose, that is what it does. Well, in this case, it's going to separate our ions. So this column is particularly a little different than a gas chromatography column. The gas chromatography column was made and structured and operated on the inside a little differently than the ion chromatography column. So that's really the purpose of this next set of lecture videos that you're going to be watching. We need to kind of get down and dirty and talk about some of the details that come along with the columns. First, what I want to say is just like many other times in many other systems, pieces of equipment, there are going to be numerous column choices for you to choose from. Now, when I say numerous column choices, what we're really talking about is something like we saw with the GC. We're talking about different widths and different lengths of the columns. And then once you choose the proper width and the length, then we can talk about what goes on the inside. So what type of stationary phase are we going to find, and how can that be modified to suit my purpose on what I need out of my instrument with my method that I'm trying to run and analyze for. So numerous columns. I'm not going to say that there are hundreds of choices as in gas chromatography. With column chromatography or ion chromatography, you're typically looking around about 50 plus choices. I would say that when you take your lengths and your widths and your different stationary phases that can go on the inside, you're a little more limited here. And the reason is because we're focused on ions. And there's only so much that we can do if we only focus on ions in our system, and that's it. So, yeah, we can change them, we can modify them, we can give you better retention, we can specialize them depending on what kind of ion that you're measuring for. But, you know, the choices just really aren't there like they were with GC. So, you do have them. They're out there. You've got a booklet with all different types of columns on the inside, but you're just not going to find tons of different choices like we found in the previous instrument. All right, so there's two different types of columns. There's two different types of separation techniques that we can look at, and you already know what those are. We've talked about these before, and one is going to be on the anion side, and one is going to be on the cation side. So the anion separation is going to have a column, and the cation separation is also going to have a column. On the anion side, I'm going to put a star here because this is kind of the most go-to feature of ion chromatography. This is why we decide to use them. Remember, the cation side measures most of the time positive things, which are classified as metals, and AA does a really good job, or now ICP does a very good job measuring those. So yes, cation capability is out there, but anion capability is really our focus with ion chromatography, even though we can do both. And you're going to hear me keep saying that and keep repeating it over and over and over. So in the anion column, what you got to understand is that there's going to be particles on the inside of this column, and those particles are the stationary phase. All right, so not only we're going to talk about columns, but we're going to have to talk about these stationary phases. And on that stationary phase, there's going to be kind of little fingers that poke out. And that's what I'm drawing here on the surface of the particle. All right, so these prongs, whatever those might be, we'll talk about those in just a second. But these prongs can be modified. All right? So one of the things that I want to say is that cation columns can have the same type of stationary phase. All right? So same type of particle on the inside, or the same. So I guess I should have drawn these red. It can be the same particle, same stationary phase. So I'll draw those the same color. And those prongs, or those fingers that are poking out, those are going to have to be a little bit different for cation, because we're separating positive pieces and not negative pieces anymore. All right? So even though the basic foundation of the stationary phase is identical, the surface is modified for us. And that surface is doing the separation. Not the actual particle, but what's on top of the surface of the particle. That's kind of the key player here. What they've begun to find out is that certain stationary phases can actually accept these prongs, or these fingers, different ways. So even though I've said that these two things can have the same stationary phase, don't be surprised if they don't. Right? And the reason is because there's certain fingers that we have to attach to those particles on the anion side, and there's certain fingers that we have to attach to the particles on the cation side. And sometimes if we change that particle up and modify it just a little bit, we can get different modifiers or fingers on that stationary phase a little bit easier. So just keep that in mind, but they can be the same if they need to. All right, so for the anion analysis, we are pumping negatives through the system. So negative particles go into the system, and negative is going to eventually come out of the system in different clumps or in different groups. I'm going to have to separate the negatives from each other. All right, so we kind of mentioned this before, but in the anion side of the house, these fingers that are poking out. So here's my particle, and then I'm just going to draw these fingers poking off of the particle. If these particles were negative all the way through, then what's going to happen is that this component that comes into the system that carries a negative charge, they're going to kind of come around the stationary phase, and they're, whoop, no, I don't think so. Sorry, I'm just going to flow right on through the column because those are negative and I don't want to hang out with them. They're bad news for me. We're not going to get along. So the anion columns do not have negative charges on the inside of them. All right. Instead, what they have are positive charges that are on the outside of that stationary phase. That way, these particles can come into the system, and these particles go, oh, look at here. I've got some positive I can hang out with. And I'm just going to stay here for a little bit, and I'm going to take my time and see how they're doing. And then I'm going to kind of go on to maybe the next one, and I'm going to take my time here and visit a little bit and have maybe some sweet tea on the front porch. No big deal. Great summer day. And then we go on down and we see another particle, and I'm going to kind of stay there. All at the same time, some of these other particles might be just kind of driving through. They might kind of come around and hang out for a little bit, but not too much. And then they just keep on going. And then we get our separation of the negative anions for us. And that is how the stationary phase works. Finally, sooner or later, this is going to kind of venture off on down through the next particle or out of the column, depending on the position where it's located inside of the column at that particular point. These positive pieces, the positive pieces are typically going to be quaternary ammoniums or quaternary ammoniums. So quaternary ammoniums. What that basically means is that it's kind of like an NH4+. there's my positive charge. The nitrogen can handle 4 bonds. I mean, that's not a problem for it. It's kind of natural sometimes to see nitrogen that way. But I want you to also keep in mind that this doesn't have to be hydrogen. It can also be just a random alkyl group, and that can be an NR4 instead of an NH4. So this is just an alkyl group, which means just a carbon-based. It can be 1 carbon, 2 carbon, 3 carbon, 4 carbon chains. It doesn't really matter, but it's a nitrogen that carries with it a positive charge because it's got 4 bonds to something. Now, out of the stationary phase, that quaternary ammonium, NH4 or NR4 really is what we're talking about here. These R groups, they tend to come to us in 2 different forms, and this is going to be a simple methyl group, right, just a 1 carbon chain, or it can be a 2-hydroxy ethyl. Ethyl is a 2 carbon chain, 1, 2, and then we're going to see a hydroxy coming off of it. So that's kind of what we're going to end up seeing on the stationary phase of these particles in the anion side of the house. All right, so what I want to kind of show you is a picture, and maybe it's a picture a little bit better of what I've drawn here on the screen, but it's a picture of the stationary phase on the inside. So what you're seeing now on your screen is really a better representation of the stationary phase. So what you're seeing is that here's my column, right? And on the inside of the column, we have this packing material. And this packing material is going to be changed up depending on what type of column that I have, of course, right? That's the stationary phase that we're talking about. And they're enlarging that picture up, right? So here is 1 particle of the stationary phase. And off of the surface of this particle, what we have is basically a loaded down version of some fingers that might be pointing off. All right. So here we have some anions that are coming into the picture. So here's an anion. There we go. And this anion is coming in and it's going to go, hey, look at here. I see some positive, and I'm going to kind of sandwich right on in there for a minute. And it's going to hang out there for a while, and then sooner or later, it's just going to kind of pop off. But, we said that there's 2 kind of R groups that are on these nitrogens. One is an OH group, and the other one is just a complete methyl group. That's all that it is. And if you kind of take a look at this picture, you're seeing some OH groups that are loaded down on here, right? Now, this could come from the stationary phase, or it could also come from your mobile phase. Your mobile phase has water in it. Your mobile phase could have some base in it, NaOH or KOH, and those OH groups can sit down on this particle and kind of take up space as well. It's no big deal. I mean, those OHs are going to hang out for a little bit, but as you can see in this representation, these OH groups are kind of popping off too. So they're just kind of making room for the other anions that want to come into the picture. So we get this positive charged particle, and the positive charged particle will lure the negative anions to it, and they will hang out and they will get delayed, and that will increase their retention time and start to separate them from each other. The issue, though, some people have is that they forget that the mobile phase is typically alkali, or it's got an OH group in it, or it's slightly basic. And even the water can kind of associate with the surface of the stationary phase particle. Well, it's no big deal. It's not going to interfere with anything at all. So you're okay with that. But that's why some of those OH groups are listed. Yes, the OH is part of the ammonium, but the OH is also coming from your mobile phase as it saturates the column and as it goes through. Over here to the right-hand side, you kind of see an enlarged detail of what's going on the surface of the particle. So here is the particle of the stationary phase. Remember, we've not really talked about what that particle is yet. We've only talked about the prongs that kind of stick up. And this prong is going to be an R group, and on that is a nitrogen with maybe 3 other R groups. And those R groups could have OH groups. They could be anything they want to be. They could be methyls. They could be ethyl groups. Who knows? That's where some of our choices come into play. And this OH group is going to kind of hang out with that positive nitrogen, and that's what's going to get replaced when another anion comes through into the system. All right, so there's kind of the surface of the particle, and that's what's going on if I took my microscope and kind of zoomed in to a little bit of closer of a detail. Here's another kind of simulation of a stationary phase, and these are the particles that are inside of my column. And what you're seeing is that the surface of these particles are loaded down with positives. I mean, I see the positives kind of stamped all over the surface of that particle as we go through. Each one of these balls are basically representations of different anions that are coming through the picture. So, you know, chlorine could be the green color, iodine could be the purple color, bromine maybe could be the red color. I'm just making all of that up. It can be anything that it wants to be, but they're different. And as you're seeing, these red ones seem like they're not sticking to the surface of the particle as much, right? It looks like if I take a look at the colors, here's a red, there's a red, it's not stuck. There's a red that's not really stuck. Here's one, there's one, here's one. These things are not really sticking to the surface of the particle, right? I see one right here, but that's about it. Maybe one right there. Who knows? But that's about it. So these red ones are not associating themselves with the stationary phase. And if I take a look at the column and I assume that the flow happens from that point to this point and out, then I'm seeing that the red color is starting to separate a little bit more. And that's because it does have no association with the stationary phase. The retention time is going to be very short because it's not spending a long amount of time in the column. Now, if you take a look at the purple ones, there's hardly any purples that are free out in the solution, just outside of the stationary phase. It looks like every single purple particle that I see on the screen is going to be stuck to the surface of that stationary phase. And I also see the green has a tendency too. The green is getting stuck. The greens on there, they're not like the red ones. So this purple and this green color might be a little bit harder to separate. They might come out a little bit closer together versus the red one that is fully separating itself from the stationary phase. So hopefully that gives you a better picture of what's happening on the inside of the column, and visually maybe what a stationary phase particle is and what we're trying to talk about as far as retaining the anions. It's all about the surface, and this is typical in your anion exchange column, and that's what you're seeing right here. So anion columns have positive stationary phases because that is what's going to separate your anions from each other. Okay, cations are going to be a little bit different, and we'll talk about those in the next video.